Great. Hey everyone, welcome to the Section 3 Tackling STEM webinar. Uh, Good to have everyone here. I promise not to take too long of your Saturday night. I guess this is sort of a very informal sort of webinar, and I don't want it to be like a sort of a conference type style. So please chuck in the chat or the Q&A if you have any questions, or if you wish to unmute and talk as well, that's okay as well. Cool. So I'll just introduce myself, tell you a bit about what I do, and then we'll just get started with, we'll ask you a couple of questions and then we'll get started with the rest of the webinar, okay? So my name is Ange. I'm currently one of the Section 3 managers at Frasers. So I oversee a couple of, or if not all of the Section 3 that Frasers produces and shows to the rest of GAMSAT takers. And other than that, I tutor Section 3 and interviews here and there. In terms of outside Frasers, I'm a third-year med student at Monash, but went through the same sort of process that inevitably everyone will go through with the GAMSAT, GEMSAS, and was fortunate enough to sort of get a place at Deakin and Monash and ended up with Monash. And that's sort of my journey towards medicine. But I am aware that the GAMSAT is being used increasingly for a variety of purposes, not just medicine. So, it'd be good to hear if anyone is using this for a different purpose. It's always interesting to hear. Other than that's sort of my journey and what I do. And this webinar is essentially going to be focused around Section 3 strategy and sort of what to look out for in STEMs and things like that. Before we progress, I don't have any formal slides. I was just going to show a couple of STEMs, get some feedback from them, and then sort of work through them. Could you chuck in the chat if there's anything in particular that you'd like me to cover? Or any questions to start off the discussion of today's class, or any questions or anything you'd like addressed? Is everyone sort of sat the GAMSAT previously? Is this the first time? First time. Okay. First time. Logarithms. Sure, I can give you a quick tut on it. I don't have a STEM on it. We get a couple of sort of queries through the Instagram sort of interactive things for abstract stems. So I have one of those and a quick sort of a simple data graphy one. Don't have any hereditary ones on me, but there should be more in our question bank if you have access to that. But cool. Given that it's the majority of people's first, or majority as in 5 people, it's their first time doing it. Any particular questions that you have that you would like for me to address? Recording will be on the Atlas after it's after the session, and you'll have access to that if you signed up. Not to our courses, it's just the free one. Yep. Any other questions that you want me to address? So there's one about hereditary complex organic pathways. Great. Managing time for Section 3. Approach to questions. Sure. So we'll start off with the hereditary sort of questions. Now, don't have any particular ones on me. I can try and look towards the later part of our session. But with hereditary questions, it's unfortunately the part of the GAMSAT that really requires that sort of prerequisite knowledge to be used and utilized. And that's the only part of biology that you sort of really need to have a basic understanding of. If you're sort of sitting here not really sure what those stems are about, I would sort of, the basics that I would know would be how to draw up a Punnett square, how to sort of have basic sort of modes of knowing your basic modes of inheritance, you know, your autosomal dominant, your autosomal recessive, sex-linked dominant, sex-linked recessive, and sort of like your why you know, inherited diseases and whatnot. You don't need to know the diseases in particular, just sort of how the inheritance comes about. Knowing how to read a pedigree chart would be useful as well. But other than that, it's the basics sort of genetics that you would get from Khan Academy or our essentials. So you don't need to know everything. It's the very basics of just doing up a Punnett square, knowing what a genotype is, and being able to work with the information that's in front of you. The majority of genetic stems and hereditary stems you get will be maths based, because genetics in and of itself is just predominantly maths. So you'll be working with percentages and ratios. So if you are uncomfortable with hereditary questions or genetics questions, I would maybe take a step back, maybe start to think a bit about if you're comfortable with ratios and formulas, not formulas, ratios and percentages, because that's what they're testing. So I hope that answers that question. I understand I can't explicitly answer it without doing a question, so I'll try and find it towards the end. And we'll move on to the second sort of question in the chat. How do you manage timing for section 3, and any advice on approaching the questions? So I'll just sort of quickly grab this whiteboard thing that I'm assuming everyone can see. Within section 3, there's sort of two sort of strategies that I would break things into: macro and micro. Okay, so macro is more your sort of exam taking strategy. Okay, and micro is more your STEM based. Your STEM based strategy. Okay, so let me sort of go through it a little bit. I'm assuming people have done mock exams and things like that. If so, chuck in the chat, what's your way of going through it? Do you go chronologically from 1 to 75? Do you find stems that you like? Do you go back to front? It sounds funny, but I've had students do that. What's your approach? What's your macro approach? Is anyone comfortable enough to share? The only reason we talk about this is because the macro strategy can help you with the timing. You can sort of use your timing to your advantage. So there's different ways. So please chuck it in the chat. But there's different ways of sort of doing or having macro approaches. Personally, I find it easy to just go 1 to 75. That was definitely the way that I did it, mainly because it limits bias. It also makes sure that I give every stem a fair go, and make sure that I don't miss things here and there, because I'm choosing stems that I want to do first, and I'm not missing everything else. And then I figure out in the last 10 minutes that I have like 2 stems left. So personally, chronologically, that it worked for me, but other people it might not work so hard or work so well. The reason being that if the first stem that you see, if that's a difficult stem for you, that you may get a little discouraged and the rest of the exam is impacted. And that's one of the disadvantages of choosing that macro strategy. Now, in doing this, it's really important to keep to time. So I strictly abided to sort of like 2 minutes a question. And if I went anything more than that, I would just sort of, I'd stop, put down an answer and move on. To me, it was more important to attempt all 75 questions than sort of, choose a particular bunch that I was definitely going to get right. Personally, I found that it was difficult to know whether it's definitely correct or not. Sometimes it's a very obvious answer and everything else doesn't make sense. Sometimes it's just very ambiguous. So, with that approach, it's really important to stick to time. and sort of let go of that sort of perfectionistic mindset that you're going to get everything right. If anything you take away from today, please take away the fact that you cannot sort of get like 75 out of 75. I don't think anyone has. Even the people who score 100 in section 3 get roughly like 60 to 65 out of 75 or something like that. Questions are meant, some questions you're meant to make mistakes on, you're meant to get wrong. Okay. So the first strategy really banks on the fact that you let go of that perfectionistic mindset, you give it your best go, you get down to a 50-50, you choose your answer if you're running out of time and move on. Okay. So this is one strategy, and that'll help you with the time management aspect of the exam. The second sort of strategy that I see is the block method, right? The block method is where people go, all right, like I'm going to do questions 1 to 20. And that's going to be a good 40 minutes. Okay. Or if you can't focus for that long, that's fine. I'm going to do questions 1 to 15, 16 to 30, right? And so on and so forth in 15 questions intervals. Okay. So within your 15 questions, you spend half an hour on it, take like a 30-second breather, move on to the next set. And within that set, people tend to choose stems that they like and do them first. So let's say within questions, 1 to 15 housed, I don't know, 4 stems, okay? And let's say I order them, so 4 stems, 1, 2, 3, 4, and I order them in, the way that the order that I like and I find easiest. So I might do stem 3 first, 2, 4, and then finally I might do the first one. Okay. But I do all of these within the time limit of 30 minutes, but I'm still choosing within the set which ones I like and what I like to do. I tend to see that this is the optimal sort of strategy, mainly because it makes sure that you're staying within time, you're attempting all the questions, but you're also playing to your strengths a little bit. Yeah. So this is sort of the second strategy. The third strategy is to just go through the entire exam during reading time, find the ones you like, do them first, and then do the other ones that are remaining. The only disadvantage I'd say is things that you look at, like if you look at a STEM straight away and you think, yeah, that's easy, like I'm going to fly through this, and then you read the actual thing, you get to the actual questions, and they're really difficult to start off with, right? And this is the sort of gamble that you take with choosing approaches like that, that you're not, you don't know 100% of the time what something's going to be like when you get into it. So that's just a disadvantage to keep at the back of your mind as well. Okay. So this is the first strategy. This is the second strategy. This is the first. The third is just to find ones you like, do them first, and then do everything else. Also be aware that you don't want to miss questions. That's a second sort of biggest disadvantage within that strategy. And I guess the last strategy is to do it by science. I say it's the last because it's getting more outdated. No STEM has one particular science that it's testing. And because of that, it's harder to sort of, know that this is a physics STEM just because it has a formula, but when in reality, all the questions are about how the relationships within the formulas than the numbers themselves. So that's sort of the last strategy. So those are the macro strategies that I was talking about, and the macro strategies will help you sort of stick to time and sort of have a rigid sort of structure within your time, right? There's a couple of strategies within the chat. Typically sort of starting with bio because you find them easy, moving into the rhythm. Yeah, that's perfectly fine. Again, be aware that the ones that tend to be tricky within the GAMSAT are those long-worded bio ones. They start off with very theory-like questions, and then in the middle they throw in a formula and it becomes suddenly maths, right? So just keep aware of the strategy, know your limitations, but at the same time, be very certain that you're going to have a macro strategy. Going into section 3 without a macro strategy is sort of it's like you're going into a dark room, and you can't, like, you basically can't see anything. So please have a macro strategy in the way you go about the exam. It's really important. The micro strategy is going to help address the other questions within the chat. So the other question was sort of about complex organic pathways. Now, complex organic pathways, that's definitely a type of STEM within your within your micro sort of strategy. So within complex organic stems, can someone chuck in the chat what they find most difficult about organic chemistry stems? Can you chuck in the chat why that's a challenge? Functional groups. Unfortunately, functional groups is just sort of something that we need to memorize and need to know. There are some pivotal ones I will chuck in the chat later, but processing info, lots of pictures and info language, cool. Would I be fair in saying that there's always a paragraph that describes the mechanism of the, yeah, and there's always a paragraph that talks about the mechanism of the picture or the pathway that's there. And then most people just lose track in that pathway because it starts to talk about nucleophilic addition, attack, and all this oxide ions and all this stuff, where it just makes no sense. Am I fair in assuming that that's where people get stuck? Yeah, great. So I say great because it's all the same pattern, right? So complex organic chemistry, like the major skill that's being tested there is visual reasoning, nothing else. So visual reasoning being a fancy term for just pattern recognition, right? So things to look out for within organic chemistry pathways are your rules and concepts. So sometimes within the stem itself, you might get a sentence that says, this reaction takes place, it only takes place in acidic conditions. That right there is a limitation, right? So what that does, it essentially limits the scope of the stem, right? So it only happens in acidic conditions. I promise you, one of the questions will be something happening in a basic condition. It'll give you all sorts of wacky diagrams as options, and one will be cannot be determined. And that will be the answer because you don't know what this reaction is going to be like in a basic condition. It can only happen in acidic, right? So majority of organic STEM questions, the first thing you look out for are rules and concepts. It happens in acidic conditions. When this gets added to this forms. So you want to know what are your basic inputs, what are your basic outputs. Treat it like a pathway, and that'll help you sort of understand the broader mechanism or the workings of this entire pathway. Okay, so rules and concepts really important. Inputs and outputs. The third thing that's sort of important, and I think this is all for organic chemistry really, is example similarity. So what this means is uh, whatever example that they give within the whatever example that they give within the stem itself, the answers and the mechanisms with which they want you to work and think through are very, very similar to the mechanism they've shown in the stem. Okay, so it's nothing weird and wacky that they're trying to throw at you. The pictures that are there, you don't need to sort of sit down and analyze what each part are. You need to think about what's coming in, what's going out, how do they look different. Okay, and what are the little things that are changing within each step, and that'll help you understand what the entire reaction is. And the questions are all going to be based on that. With organic chemistry, there's sort of like three types of questions that can occur. It is like you have the product. Here is a product that was formed by I don't know, I'm going to name this reaction, the Claisen-Clope reaction, which is an actual reaction, right? As a result, here is a product of the Claisen-Clope reaction, okay? What are the reactants? Here's the product, what are the reactants? The second thing you can be asked is, what are the products with the given reactants? And the third thing that you can be asked probably is based on context, right? So your worded statements, which of the following statements are true? This can happen this can happen in acidic conditions. This can happen, etc., etc. Okay, so within organic STEM questions, there are three major things that can be asked: reactants, products, and something based on context. Okay, And majorly, the things you're looking out for are you're looking through a lens of pattern recognition. So you're looking for the rules and concepts within the stem. Look at your mechanism, look at what's going in, what's coming out, look at how they're looking differently, and sort of try to understand what's changing within the example, because and use that as a framework for getting into your questions. Okay, so that's sort of my advice for anything based on organic chemistry. They're all the same. I promise you, all the stems within organic chemistry are the same. They're all based on these three things and these three questions. Okay. The functional groups that are sort of important to know, know your alkyls. Okay, so your methyl groups and things like that. Know your alcohols, know your carboxylic acids, know how they look, know your ketones, and know your aldehydes as well. Other things within organic chemistry, your alkenes, alkanes, things like that. These are very, very basic, very, very important to know as well as your amines and your amides. Cool. Does that help with regards to the question on organic chemistry? I realize I've just spent a bit too much time on the questions within the chat. Would you guys be interested in going through an abstract sort of question or STEM that I picked out? Yep, cool. Easy. So this is one of our stems. Am I sharing this? Can you see my OneNote? So question, should pattern recognition be similar approach for physics related stems as well? So physics is a bit different. So physics is essentially analogous to maths, right? It's using whatever prereq knowledge you got from your maths and sort of applying that. So it doesn't like link too much with pattern recognition through visual lens, but it does link with like how you can sort of look at a formula. I think I'll get to this later on if we have time. Yeah, it's physics is a new ballpark. Cool. So this is one of our stems from one of the mock exams that we have. I'll give you maybe a minute to have a read and, let me know what you think about it after. And let's chat about approach to stems. Okay, so I'll give you a minute. All right. So how are we tracking? How are we? Am I on mute? Yep. How are we going, guys? Do you need another minute? Yep, recording's going to be on the atlas or whatever. You'll get sent a link to the atlas, and that'll have the link for recording. Yep, just the stem. How'd you find the stem? Great, cool. How are we going with the stem? What did you guys think about it in terms of the content? Pretty straightforward, pretty simple, difficult to digest. Is okay. Okay so far. Great. All right. With that said, then let's difficult to digest. Sure. Okay. So with that said, oh, actually, this isn't very well thought out. Put this question over here. So you have the stem, you have the first question. Have a go at the first question. We'll come back and we'll try to sort of digest the stem and talk about approaches to stem. So I'll give you 2 minutes. Okay, so I'm just going to launch a poll. Can everyone? Oh, I'm muted. Sorry, I've just launched a poll. So just chuck in the answer that you think is correct. Cool. So I've got about half the people submitting. It'd be good to get some more answers to see what the range is like. Get some more data. So I'll give you 30 seconds. Just chuck it in. It doesn't matter whether you think it's right or wrong. Almost. Great. All right, so I'm going to pause it there and the poll. So you should be able to see the poll results, hopefully. So can we see that about half of us have chosen A and the other half have sort of been spread across B, C, and D, with a quarter of us choosing C. So very interesting. We can either do two things, and you let me know what's more helpful for you. Would you like me to sort of go through the STEM itself and try to break it down, or try to go through it as I would on the day? Or would you like to head straight into the question? What would you find more useful? Beauty. Okay, so we'll go through it as we would. All right. So I'm gonna keep chat here. All right. So I'm going to time myself because I feel like it might be more realistic to time. So I'm going to time myself for, I said 2 minutes a question, so I'll keep it. Oh, you can't see it. I promise symbolically that that's 2 minutes. So I'll start it and we'll go ahead. Okay. Okay, so I started it. So Leonard-Jones potential is a mathematical model that approximates the net intermolecular potential between a pair of neutral molecules. Okay, the model is based on the interaction between the electron clouds of both molecules. When two electron clouds overlap, there is a net repulsive force expressed as a positive intermolecular potential. Okay, interesting. So when molecule 1, molecule 2 overlap, there is a net or I'm not going to do that. So I'm just going to write net repulsive force, and then my intermolecular potential, I'm just going to write potential as voltage, right? Potential as, what is that saying? Positive. Okay, great. However, when the molecules are separated, there is a net attractive forces. Okay, so this is molecule 1 and this is molecule 2. Then this is net attractive, and therefore my potential is now negative. Okay, the Leonard-Jones equation incorporates both these phenomena and is given below. The equation can also be used to generate the plot shown in figure 1. Whenever there's a reference, I have to look at the figure. So here's my potential, here's my separation, internuclear separation. Okay, so I'm assuming that's between this the two nuclei, and that's the separation distance between the two nuclei. And I have a bunch of symbols I don't know, but they're sort of similar to the ones I see in the formula. Okay, cool. So the van der Waals separation, which is the sigma, great, occurs when the electron clouds of two species first interact, and there's a finite distance at which the intermolecular potential between the two molecules is 0. So at sigma, the voltage is 0. The bonding radius describes the distance between two separate molecules from the center of each nuclei. Okay, great. So that's this here. So internuclear separation. That's also sort of the bonding radius on here. Okay, sure. The well depth is a measure of how strongly. So I'll pause it there. I'll keep going with time. Okay. And describes the well depth is a measure of how strongly two molecules attract and is typically at optimal bonding radius, at which the bonding pair is said to be at equilibrium. Sure. So well depth is a measure of stability, okay, or strength. Cool. I've finished reading my STEM, okay? So it's taken me about 2 minutes and 15 seconds, all right? So let me sort of move into my question and not take too long to sort of, yes, it's going. So let me go on to the question and try and see where I can use my notes, if anything, or go back to the STEM. So the first question, which of the following best represents the term used in Leonard-Jones potential equation? So this is directly linking to the equation. So therefore, most of the other things, I'm just sort of drawing a blind eye to. It's talking about the equation, I go to the equation to describe the attractive forces between two molecules. Okay, so what have I written down that's linked to it? Well, I've talked about attractive forces here. I know that when my sort of force is attractive, or net force is attractive, I know that my potential has to be negative. So this is linking it to the equation. So therefore, I have to look particularly at this and try and see what part of the equation is negative, right? Because I know that whatever part's negative is going to be indicative of an attractive force. So I can see that the only negative thing naturally is this part here. So therefore, this part of the equation simulates an attractive force. So therefore, the answer should be A. Okay, and I'll move on. So it's taken me about 3 minutes, okay, to finish this with talking, with explanation, to get to the answer A. Okay, any questions about the breakdown of that? The reason I wouldn't probably go for C, okay, is mainly because it sort of looks like a constant. I know that it's also a measure of the strength of attraction between two molecules. It's not negative. It doesn't sort of tell me anything about whether it's attractive or sort of repulsive in nature. It's just about strength of attraction or strength of relationship between two molecules. So because I don't, that's sort of two logical jumps away from the stem itself, right? So I would probably go for what's the first thing from the information I read, what's the first conclusion I can make logically, what's negative within the equation, this part here. So therefore, A must be my answer. Okay. Any questions? Any questions? Does that make sense? So yeah, good question. So why wouldn't this? So in reality, almost all of these questions or almost all of these options are correct to some extent. Okay, but you're choosing the most correct one, right? Best represents, not represents, best represents. Okay, so therefore all these options are put on a spectrum. So you have option A would probably be the best one because it is negative. It is a part of the equation. And remember, the question is also asking for term. Okay. This entire thing in the middle of the equation, okay, is a function. Okay. This is saying A minus B. That's not one term, right? A minus B. And also the thing within the middle is giving you an indication of a difference, right, between an attractive and a repulsive force. But we're not we don't care about that, right? We are only caring about the attractive force. So what best represents that? What one term represents that within the equation? That's got to be the one with the negative sign on front of it. So I'd probably say that A is there, right? I'd put probably C here, B here, not B, sorry, A, C, D here, and B as my last one. Yeah. So in terms of correct options, so A is my best representation. Okay. B is my least favorable representation. All of them are correct to some extent. You can reason your way through all of them. The most correct one is A. Okay. Cool. All good. Would you recommend taking notes during the exam? Personally, I did. Okay, and it helped me a lot. The reason being that my mind tends to waver. So in order to keep myself engaged and accountable, every time I read a paragraph, I'd stop and think to myself, what is the major concept that I got from that paragraph? Okay, and write down one bullet point that best encapsulates that paragraph. Okay, this doesn't the caveat with this is that you don't start writing sentences and you don't start writing bits of the paragraph. Okay, 4 to 5 words that summarizes that entire paragraph. The next paragraph you read, you stop to think to yourself, how did this add on from the first paragraph I just read? So you're constantly sort of questioning yourself and sort of forming relationships within the STEM. And this is the best way of staying actively engaged. There's no reason or there's no point in just passively reading the STEM or going, oh yeah, there's a figure, oh yeah, there's a formula, and then getting to the question and going, oh, hang on, I've forgotten what I've read. Right. So personally taking sort of these bullet point notes or, drawings of what the paragraph was saying was a way of keeping myself actively engaged. Okay. And it's difficult to actively engage by just passively reading it because you've done section 1, you've done section 2, and then you've come to section 3. Your concentration is already at 50%. So you want to make sure that you actively engage as best as you can. All right. Would you recommend doing it on paper or a little whiteboard? Both. I'm not sure which is more practical. It doesn't matter. Whatever you're more comfortable with. Yeah, I was more comfortable with paper, but a lot of my students this season they've been comfortable with whiteboards. So each their own. Okay, cool. Any other questions before we move on to the next question? No. Okay. All right. So I'll get rid of all of this. And we'll move on to the next question. Another thing that would be good to take away from this is the STEM does look eerily abstract. Be good to understand, like the fact that even if it was so abstract, the first question was able to be done within 40 seconds. So it's a real skill. To the person who just asked on the Q&A about the recording, it will be uploaded on an atlas that you would have gotten a link to, or the phrases community that you can join. The link to the recording will be uploaded there. So I hope that helps. Okay, cool. I didn't say anything at the start that was remotely helpful. So yes, just another thing as well, just to make sure. Oftentimes when you see a stem like this, you're sort of, you're looking at it, you're going, this is extremely unfamiliar. This versus a stem about, biological pathways. You choose the stem with the biological pathways any day. But knowing that this question was able to be answered within 40 seconds, whereas with bio questions, you're more choosing through options, thinking through them, etc., will take more time, right? So, don't have that, try not to have that bias when you look at a stem. Just go, oh yeah, this is going to be easy. Give each stem a fair go, and if it's getting difficult after you've read it, after you're attempting the questions not happening, it's fine, put down an answer and move on. Okay. All right, so let's go to question 27 and 28. So we'll do 27 first. I'll relaunch the poll, and I don't know if it's already launched, but I'll relaunch the poll. I'll give you guys a minute. Have a go. You guys can do 27 and 28 within a minute and a half. These are not, again, try and see, what sort of concepts we wrote down that are helpful here. This isn't too complex. So just pause, reflect, try and get down to a 50-50 and choose your answer. Okay, so I'll give you a minute to look at 27 and 28. All right, so that's the 1 minute mark. I would really love it if we chucked in more answers for 27. Even if you're not sure, just give it a go. Just chuck in an answer. Okay, 5 seconds. Chuck in an answer. All right. Okay. So I'm going to share the results here. So the majority of us are under the impression that we don't have enough information. Now, again, the way we go about it, try and break down the question. Okay, so we've got two molecules of xenon, and we know that the van der Waals separation between them is 4.80. Okay, what's the best approximation for the radius of a molecule of xenon? Now, the van der Waals separation, where is that seen? And this is sort of the majority of GAMSAT stems, and especially section 3, right? It's nothing more than just sort of reading the keywords within the question and then reminding yourself, where within the stem did I see that? And that's sort of a process that at phrases we like to call that mapping. So we read the stem, we sort of understand where majority of things are. We go to the question, identify the keywords, and think to ourselves, where was it within the stem? And that's the majority of section 3. It's just going sort of mapping and wearing, right? That's the majority of it. So van der Waals separation, where was that? That was at the start. So van der Waals separation occurs when two electron clouds, right, they first interact. So when the two electron clouds of xenon sort of interact here. So xenon and xenon. All right, great. And there's a finite and whatnot, at which the potential is 0. Now we know that the van der Waals separation is 4.10, but now that's a value, right? Now, what is the 4.10? The 4.10 could be here, it could be here, it could be here, but we don't know what that value means. So therefore, we can't sort of decipher that from the stem itself. So what other pieces of information do we have that can help us identify? Well, the graph. Why? Because the graph has a sigma, okay? And how is that a link? Well, the sigma is van der Waals separation, right? And the sigma itself, we can see, is on the x-axis. And what is the x-axis a representation of? R. What is R? Internuclear separation. Okay, so what is that telling me? It's telling me that sigma is basically the same definition as R, or internuclear separation. So if this is the nucleus of xenon, this is the other nucleus of xenon, then the distance between them, my internuclear separation, right, is the same as my value that I have here of van der Waals separation. That is 4.10. Does that reasoning make sense? Any questions from that reasoning? Yep, makes sense. Yep. Yeah, sure. So we sort of went, okay, the question is asking us about van der Waals separation. We went, what is van der Waals separation? Well, van der Waals separation is when the electron clouds first interact. So here is my xenon molecule here, and here is my xenon molecule here, and that's when their electron clouds are first interacting. Okay, but we know that the distance with when they first interact, that's called van der Waals separation, but we don't know what the value of 4.10, which we're given here, means. It could be the distance here, it could be the distance here, it could be within here, like we don't know what it means, right? So we need to go hunting within the stem for more information about van der Waals separation. And we know that more is given within the graph itself. We can see that van der Waals separation is here, sigma over here, and we can see that it's on the x-axis. Now, the x-axis is a representation of internuclear separation. Internuclear, break that word down. Inter meaning between, nuclear meaning nuclei. Okay, so it's the separation or the distance between the two nuclei. And we can see that sigma is on the x-axis, which means that sigma, or whatever value I have, is the value for internuclear separation, or the distance between two nuclei. Does that make sense now? So therefore, if this is the nucleus in the center, and this is the other nucleus, then this distance here is 4.10. Okay, but we don't need internuclear separation. We want the nuclei of the atom, and the nuclei is just from the center to the edge of the atom. So therefore, roughly, this is going to be 4.10 divided by 2, because it's roughly a half, and therefore this is going to be 2.10. So the answer is C. Okay, does that make sense? Any questions from that? Yep. All good. Any questions? Possibly another, a reason of just getting to the answer. This is probably the quickest way without even doing all this sort of this mumbo jumbo. Just look at the options, right? Let the options guide you. So we know that the van der Waals separation, which is essentially when the two nuclei interact, or which is essentially when these two xenon molecules interact, we know that that separation, okay, when the electron clouds between that separation is 4.10. Okay, so therefore the radius of one atom is not going to be 4.10, it should be much less, because the separation between the two atoms when they first interact is 4.10. Even if it's this, right, you assume that the separation distance is 4.10. So the radius of one atom, therefore, has to be much smaller than the separation distance between the electron clouds. So we can get rid of A, and we know it's not going to be larger because we're talking about the radius of one single atom versus the separation between two atoms. And immediately, if we needed to pick an answer and you weren't tempted to go for D because you have the relevant information, you can immediately pick C without doing any maths or without, thinking of sigma as an internuclear separation. Does that make sense? Any questions? So just to recap as to what we do when we sort of read a stem, have a read of the stem first, have a read of the paragraph, stop, pause, reflect, think to yourself, what was a major concept I got from that? Write down a 3 to 4 word summary. Move on to the next paragraph, move on to the formula. Have a read, think, okay, what is that saying? But also, what has that now added to the information that I already know from the first paragraph? How are they linked? Okay, whenever you're looking at a graph, there's not much you're looking at within the 30 seconds you have to skim read it. You're looking at the major things. Yeah, you're looking at your axes. Are they logarithmic? Logarithmic, it's nothing, just means that the increments at which the y-axis are increasing is not the same as a sort of a linear increase as 1, 2, 3, 4. It goes from 10 to 100 to 1,000 to 10,000. Okay, is it logarithmic? Is it linear, etc.? After this, think about the variables. Okay, what variables are there? The intermolecular potential, internuclear potential, internuclear separation. Think about the variables, think about their relationship. Okay, and most importantly, think about context. Okay, how does this graph fit in within the narrative of the stem itself? Okay, when I'm looking at a graph, these are the major things that I'm looking at. Okay, look at the axes, look at the variables, look at the relationship between the variables, and how does the graphs fit in with the rest of the stem. You don't have time to look at much else. Okay, so after sort of having a read, writing down your like 3 to 3 word, 3 to 4 word summary, keep reading, keep constantly questioning yourself. How does this link in with everything I've just read? Get to your question, use keywords within the question, go back to your stem and start going, okay, where did I see this? What is this linked to? And then use that context to answer the question. Okay, this is in essence a simple nutshell of what section 3 is. Any questions so far that you would like me to answer? I can't see anything at the moment. So I'll let you guys relaunch the poll for question 28. So if you can chuck in your answers for question 28, I'll give you a minute, and then we'll move on. All right, last 30 seconds. Ten seconds. Just chuck in an answer if you don't know. That's completely fine. Yep, perfect. Okay. So I'll end the poll there and share the results. Again, majority of us think it's C, which is the right answer. And some of us have gone for D as well. So that's completely fine. So does someone want to chuck in the chat how they did this question? Any suggestions? We've got one explanation. Excessively large is not meeting the condition of equilibrium. So theoretically, there is no potential, meaning zero. Okay. We've got well depth is E. Graph shows E is on the x-axis. Intermolecular potential is Y. So E occurs when Y equals zero. Amazing. Good stuff. And also, the major way of sort of looking at this is we have well depth, right? Where we've been asked for V, okay, intermolecular potential. Now, someone's asked, can you use the graph? There's nowhere where it says, you know, according to the formula, according to the graph. It says just given the information, right? What do you think? So use anything that has intermolecular potential there because that's the source of information to answering the question. So in this case, we've got two sort of suggestions. Now, given that we've got the well depth of something, it's essentially people might think, oh, there's numbers, so therefore I have to calculate something. But at an excessively large bonding separation, right, it's the x-axis within the graph that we need to look at because that in essence is talking about the separation between two molecules, or aka bonding separation. Now, at an excessively large bonding separation, someone's written in the chat, as I keep going on and on, what do you notice about the intermolecular potential? Remember that your intermolecular potential is a y-axis. So what do you notice about that? What is it approaching? There's two ways we can get intermolecular potential. We can either get it from the formula or we can get it from the graph, right? Exactly, zero. It's reaching zero. That's your answer, okay? There's nothing more to it. It's literally asking, as you keep increasing the separation between molecules, as we're doing as we keep going along the x, we can see that the curve is getting back towards the x-axis, getting back towards that zero. And lo and behold, our y-axis is talking about potential, which is exactly what we need, right? So therefore, the answer is zero. Another way of thinking about it is if you use the formula, the bonding separation, remember, the bonding radius is given by R within the formula. And what do you notice about R? It's at the denominator. Okay. If it's at the denominator, if I keep increasing my R, that is at excessively large bonding separations, at excessively large values of R, the entire fraction becomes excessively small and close to zero. Okay, so it becomes something like 0 minus 0, okay, or 0.0001 minus 0.0002, or whatever, something like that, which is essentially 0. And you're multiplying that by well depth, whatever it might be, 4 times 0.997, as it says here. Regardless, if you're multiplying anything by 0, it's going to be 0, which is, again, your intermolecular potential. Okay, so there's two ways of getting it. The easiest way would have been to look at the graph, see that it's approaching the x-axis, it's getting to 0, so therefore the answer is 0. Okay. Any questions about that? Any questions? So the major takeaway, again, from that, unless specified, use every bit of information that has the keyword in there. That's your wearing, right? You're going, looking at the keyword, going back to the stem, looking at where it is, and that's your entire mapping process. All right. So that's sort of the major takeaway from this. Are there any questions about the stem that you would like to discuss? Otherwise, would you think, what else would you like me to sort of chat about? I was going to sort of go into micro strategies a little bit. So when we have a look at graphs, this is what we look at. When we have a look at tables, what do we look at? When we have a look at formulas, what do we look at? I was going to go into that sort of thing. Would you find that helpful, or what do you guys think? Or we can just do some general question and answers. Yep, cool. So what are some major things? We've talked about organic chemistry, right? So let's do a list, right? So these are your micro strategies. So we've talked about organic chemistry. We've talked about the fact that, you're looking at your rules, you're looking at your concepts or definitions, you're looking at sort of example similarity, okay? Major sort of difference in output and input within the mechanisms. Okay, so those are the major things you're looking at for organic chemistry. For graphs, we are essentially looking at these three things, right? For formulas, I sort of find it easy to look at it in terms of these three things, okay? Outputs, inputs, and influences, okay? So what I mean by that is start looking at a formula as essentially a way of denoting variables, okay, or a way of denoting relationships. We know that the output here is intermolecular potential, but we know that there are a variety of variables that impact what the value of the intermolecular potential would be. That's how strongly the molecules are attracted to each other. That's your well depth, okay? You've got how far apart are the electron clouds and how far apart are the nuclei. And this eventually affects your intermolecular potential. What's really important to understand is the relationship between the variables. So we can see that intermolecular potential is inversely proportional to the bonding radius. So the further apart the nuclei are, right? So that means the increase in R will reduce your intermolecular potential. However, the greater your the greater your sort of well depth is, the greater your intermolecular potential. So you're looking at your inputs. You're looking at your inputs, you're looking at your outputs, you're looking at anything that might influence that. So these are your major inputs. That's your output. The thing that's influencing this is the well depth there. Yeah. So these are things to look out for in formulas. The other things that's really important are units. Sometimes units help you sort of create a formula in and of itself. So, you can use that to create a formula when the question is trying to test your synthesizing or your ability to synthesize relationships from a given paragraph. So the paragraph might say, when A increases, B decreases, right? In more complex terms. And then your job would be to go, okay, well, then A is inversely proportional to B. So if I put an equal term there, then my formula therefore becomes K over B, where K is my constant. Okay. So therefore, this is my ability to create a formula, right, based on the relationships that are there. Okay. Cool. So these are sort of the major things that you look out for within formulas. Okay. The major things you look out for within tables. Trends, right? Significance and context. So really important for looking at formulas for context as well. But in terms of tables, so I've got just like a random one here that I picked up from one of our stems. So if we can have a look at this table, you can sort of try and see that, we're using saline, we're using liraglutide and linagliptin. These are two drugs that are used to help cholesterol or help reduce cholesterol. We've got a whole bunch of variables here, and we can see that that across the row, we're seeing the impact of saline, liraglutide, and linagliptin. Okay. Now, what I would like for you to understand is it's important to notice the trend right across the table or whatnot. So we can see that liraglutide and linagliptin both have a lower whole body fat mass compared to saline, right? And that would be something that'd be really interesting to note. And we can see the trend across the table there. That's the first thing. The second thing is significance. So without doing anything, if we answer question 33, which says which drug is effective as a weight loss agent, well, for weight loss, we look at whole body fat mass, right? And then across the three things, we can see that it's plus or minus, right? So that it has confidence intervals. Okay. So we can see that liraglutide, for example, 31.42 is its sort of middle point. We add 4.8 to that, and it becomes 80. So it becomes 2, 2, 1. So 2, so it becomes 36.22. And then you take away a certain thing and it becomes 20 something. Compare that with the saline, right? Saline, which is 50.10, you add 5.6 essentially, that becomes 55.7. You decrease 5.6, right? So that becomes what, 44, something like that. So we can definitely see that between saline here and, not saline there, between liraglutide here and saline here, there is definitely a significant difference, right, between saline and liraglutide. So what does this mean? Well, you can therefore conclude, because none of the values are overlapping, we can say that it's statistically significant, or it's proving to have a significant effect on whole body fat mass. However, if we look at, for instance, linagliptin, 42.3, and we're adding, let's say, 3.8, right? 3.8, so that would be roughly 46.1. Okay, 46.1. But can we see that within, so 46.1, right, which is, a potential impact of linagliptin, we can see that 46.1 will lie within this range of saline. Okay, lies within the range of the numbers within saline. So what does that tell me? Someone check in the chat. So does that mean that linagliptin is proving to have a statistical significant effect, or does it mean that it doesn't have a statistical significant effect? No statistical, exactly, because the value here, okay, is one of the values that saline also produces. Because these values overlap, you can't tell the difference between linagliptin and saline. Okay, so immediately, you know that the answer therefore has to be A, right? Liraglutide. Okay, without reading the rest of the stem, this is just from looking at the data. So from looking at tables, you look at the trends, you look at the statistical significance, right? And often significance is given by plus or minuses within tables. You also look at the whole context, right? Like if we move on to the next question, you don't have to do it, but it's essentially talking about what's better in the treatment of hypercholesterolemia. Well, then we don't know, because there's a bunch of measures of cholesterol. We don't know what is the best measure of, treatment of hypercholesterolemia, but that's something that, the stem will tell me. The stem, incidentally, notice that in the last line here, it says that the ratio of HDL to LDL or LDL to HDL is a useful indicator of cholesterol health. So therefore, we'll be looking at this ratio to see which drug has the most impact. Okay. Immediately, you sort of know your answer. And that this is going to be linagliptin, because you can see that, it's the same intervals and the same values for saline and liragliptin or liraglutide, right? So you know that A and B is going to be your answer, mainly because this is different to this and this, okay? So we wouldn't have been able to get 34 were not for the context part of things we need to look out for within tables, okay? So within tables, again, looking out for the trends, the significance, and the context, okay? So the question says effective, like question 33. Yep. Effective. Yep. Yeah, exactly. Which is statistically significant, because you want to see this is the effect of saline, liraglutide, and linagliptin on whole body fat mass, right? So what is effective? What actually creates an effect that's actually plausible? Well, liraglutide, okay? Because it doesn't impact on the effect that linagliptin and saline has. Yeah. And that's to tell you that something has an effect, you look at the significance, which in this case, you're looking at the ranges of the values. Okay. That was sort of, that's sort of the major things to look out for within tables. And these are sort of your micro strategies to have at the back of your mind as well. When you're looking at organic chemistry, these are the things to look out for: graphs, formulas, tables. These are the things to look out for. So I hope, just mindful of time, I hope that's been helpful. I'll sort of, if they all didn't overlap and thus all significant, the most effective be, with the largest weight loss, essentially. Weight loss, the largest weight loss. Cool. All good. I'll sort of stop my sharing there. I hope it's been helpful. Let me know in the chat if there's anything else you'd like me to address in the last few minutes. How would I recommend using reading time? So for reading time, personally, I just sort of started doing questions. Now, this ultimately depends on your macro strategy. So if your macro strategy is to choose certain stems to do, and it's sort of like choose certain stems to do, then it'd be worthwhile using that reading time to sort of go through and pick the stems. That's a worthwhile use of your time. The second thing you can do during reading time is sort of mark down which questions you want to avoid, which is the alternate of the first option. Personally, I just sort of started doing questions. I know you can't write anything down, but it'd be good to sort of, you can move your cursor and stuff. So I'd sort of try and pick out concepts using that, using my reading time. I hope that helps. Any other questions? I'll stop the recording.